All right, we're going to switch gears a little bit and we're going to be talking about compression in this one, which really fits into our unit where we're talking about binary. We looked at pixels earlier in the unit and talked about the RGB color model a little bit. Let's get into it. I think you're going to like this one. File compression is the process of packaging a file or files to use less disk space. For the most part, file compression is achieved by locating patterns or redundant elements and either cataloging those elements or removing them completely. This has got to be the key thing here. We're looking for stuff that repeats for the most part, or is at least extremely similar when it comes to pictures. More on that later. Okay, so for this, I have this text compression activity that is at code.org. There's a link in these slides, but you could probably just Google text compression code.org and find it. Here's a URL if you're super interested. And we'll get into this activity. They have an associated video with it featuring Aloe Black. I highly recommend watching this video. Okay, so now's a good time to pause. I'm going to put an annotation thing that'll go maybe directly to the video, and you can watch this. But they're going to explain how the compression widget works. Okay, over here we see compressed text. We see, really this is the original text here. And right now it takes up 240 bytes. Right? There's nothing quite in our dictionary, more on that in just a second. In total, we consume 240 bytes. The original size was 240, which is about to change in just a moment. And this is probably going to be the most important number. This is the one that you want to strive to get as high as possible, is the percentage. Okay, what's going to happen is if you take a look, there are redundant elements in this text. For instance, the word didn't know, right, shows up here, didn't know shows up here, it shows up here. They're using underscores, by the way. Those are just spaces. In fact, when we type in just a moment, you can do space or underscore and get the thing. So let me show you what I mean. Effectively, each character is a byte. We got 240 characters here. Okay? A lot of them are redundant, though, right? This segment in particular, right, consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 characters, but it repeats several times. So here's what we're going to do. Over here in our dictionary, we're going to catalog that repeating text. I'm going to type in didn't know. And you'll see that as I'm typing, it is replacing the text over here in our compressed stuff. All right? So this dictionary works like a dictionary would in real life, where you have a word and then an associated definition. That's the idea here. This little sun symbol is our word, and this is the definition. You could also think about it as a key and a value. Okay? So effectively, here's what happened. I am, in my dictionary, setting up this key value pair, and everywhere where didn't know occurred, we've replaced it with the sun. Okay, this sun symbol is going to occupy one character in my compression text, right? But what it represents is 11 characters worth of stuff, right? So this is, I am basically replacing 11 characters with one character. So each occurrence, I'm gaining effectively 10 bytes, 10 characters, right? Now, there's a little bit of an offset here. We actually have to store the dictionary as well. So if I were to send this to somebody and it's just this, right? There's just this garbage sun symbol. They don't know what sun symbol means. That's what the dictionary is for. I need to send the dictionary along with that. So that brings us back over here to what we're measuring. 170 bytes is all of this, including the little sun symbols, right? That's how many characters are here. 12 bytes is my dictionary. The 11 characters for the value, and then the one character sun symbol here, right? In total, the 170 plus the 12, because I need to send the compressed text and the dictionary together so they know how to decode it, decompress it. In total, that's 182 bytes. Notice that we are effectively compressing. We're actually gaining some space because the original was 240. Okay? So again, let's look for something else that repeats, right? Something like was lost. Sorry, I'm going to pull up a photo from previous ones where people have done extraordinarily well. I was underscore I underscore was. Okay, I have created a new key pair in my dictionary, right? We see a separate symbol is created from that. Now, what's cool about this is once you get symbols in the dictionary, you can actually reference those later. What do I mean? Well, my next entry is going to be underscore sun umbrella lost underscore. Okay, so simply put, like this sun, this umbrella, they were part of a larger repeating thing. Let's back this up maybe, right? You can kind of see it here. It's nice once we have the symbols in, right? We see I underscore sun symbol umbrella lost underscore sun umbrella lost. So it starts to repeat. I'm going to bring it back. Sorry, I got to copy these guys again. Notice our compression got even better, right? We still have to have the compressed text, we still have to have the dictionary, but overall, this is better than what it originally was at 240. So what we want is for this number to be as high as possible. And if you're into this kind of thing, I recommend you keep going. I'm going to reveal a solution that I have. I'm not saying it is the best. I'm saying it is the best that I have encountered. That is one that a student has produced. Now might be a good time to pause if you want to try out to see how high can you get this compression number. But I'm going to finish this out. I have little snowman, this guy. Hopefully I can copy him from here. Copy him from here. Umbrella underscore when I'm underscore and underscore all underscore. And that brings us to a total compression of 44.58. If you can beat that, by all means let me know. Hit me up in the comments below. Send me an image on like Discord or something. I don't know. I would love to see it if you can get better than this. Okay. Another good one is this third option, the Man by Aloe Black. Reset the dictionary. But there's a lot of repetition in this one. I think you can get almost like 60%, maybe more, in terms of compression. I don't unfortunately have I don't have an image for that one. But see how high you can get on this one. Hit me up in the comments. Let me know what you can do. Okay. So that is effectively text compression, right? We're looking for redundant elements and basically replacing them with something smaller, cataloging them in a dictionary. What's important to note is this is going to be lossless, right? There's going to be two types of compression. It's going to be lossy and lossless. I'm going to skip past my image video and talk a little bit about this real fast. So data compressed using lossless compression suffers no data loss, so it can be decompressed back into the exact original. What do I mean? When we send them the text compression along with the dictionary, they can decompress it and get the literal exact thing back. That is super important when we're talking about text, right? Because you can't afford to lose any data. Lossless compression is the technique of choice for things like text files. We're talking TXT, docx, Excel files like spreadsheets, right? We can't lose any of those characters because if we did, everything just kind of falls apart. Now, there are going to be some image formats that are also lossless. And for that, I recommend watching this compression video. Again, I will put a link in our video so that you can find it. But here's the number ranges I kind of recommend, right? 0 to 255, and then 5 minutes and some change to 12 minutes and some change. They're going to talk about image compression. And images can be lossless or lossy. Now, if they're lossless, they're going to use something known as run length encoding. And here's the idea. They talk about in the video, but we're going to basically look for runs of pixels in this case that are repeating. Okay, I've got a good example over here. We got Mario, and he's very 8-bit. and there's lots of repetition in here. We're going to be looking for runs of pixels that are the same. You could or could not count these whites depending on the format, depending on if they can use a transparent background. Okay, but what I have here are 5 white pixels in a row. Now each of these pixels actually takes up a lot of data. When we're looking at text, right, we're talking about each character in text takes up only 1 byte. When it comes to a pixel, however, right, each one of these has a red, green, and blue value associated with it. Each one of those is a byte, which means that each pixel is 3 bytes. Right? You can effectively get the size of this image, right? The amount of data that it takes up, it's raw data that is uncompressed, right? By just counting the number of pixels, multiplying by 3, and that's how many bytes it would take up, uncompressed. Okay? So images are going to be a lot more data intensive than your text files. Now, with that in mind, I hope you can maybe imagine video would be insane, because all video is images really quickly, one after another, plus audio, right? So video gets real massive because we're talking 30 to 60 frames per second. That is 30 to 60 images a second, right? That's this times 30 or 60 a second over the course of, several minutes. Like, videos are in theory really massive, but they have a lot of redundancy, which means they can be compressed. So let's talk about this guy in terms of run length and how you can have lossless compression with run length. So think back to our text, where we're basically finding a repeating element and then making a catalog of it. This is going to be kind of similar. I have this repeating white pixel. Instead of putting this in here 5 times, what I'm going to do is add an extra byte of data, a number, right? I would say 5, and then include 1 of the white pixels. Okay, so what that amounts to is, right, each one of these is 3 bytes, remember? So just this one sequence is 15 bytes. But with run length encoding, what I'm going to do is add an extra byte, right, to track the number 5. And then one of the pixels, which is going to be 3 bytes. That's a total of 4 bytes. So I just replaced this 15 byte sequence with the number 5 and 1 pixel, right? 4 bytes. Same thing here. I have 5 reds in a row. So immediately following my 5 white, I would come in here and do 5 red. And that would be however many pixels. And then we go to decompress it, what we would do is we would see the number, we would then see the pixel, and we would know to replicate that pixel that many times in a row. Right here we would have 6 white, so on and so forth. Now, in theory, this could actually add data, right? Keep in mind the extra byte, the number that I added. Well, in order to keep this format succinct, right? In order to make this work, you got to do it for every pixel. We would do 5 white, 5 red, 6 white. We would keep going. We'd get here, we're looking at 3 brown, 2 yellow, 1 black. Okay? So this black, it was only 3 bytes, right? But I'm going to add the extra byte, the number, to help me keep track of it. Well, that actually increased my data here. But hopefully you'll recognize that for most pictures, we're actually reducing the overall file size by doing that. So that is effectively run length, and the idea, it's lossless. You can actually reproduce the exact image by doing so. But we are, again, looking for redundant information. In this case, sequences of pixels. Now, so here's our example of lossless formats. Our text files, PNG is a lossless format. BMP, bitmap, is a lossless format. However, there is lossy compression. Okay, this is achieved by throwing away some information. It's hard to demonstrate with this image, which is why I really recommend you watch this video. Okay, they go in and talk about how you have an image right? I mean, this is like an 8-bit color format. Realities are there's only so many colors that you can represent here. When we're actually using RGB, using 1 byte, we can actually achieve like 16 million, I believe, maybe 32 million different colors. I don't recall off the top of my head. Okay, this has like 6 different colors. So in practice, you're going to end up with a lot of possible colors. We'll say 16 million. A lot of those are going to be very similar, not quite the same. Like imagine if this black and then the black next to it are just kind of varying shades of black. Not quite the same, but they're close. So effectively, what a lossy image technique would do is it would kind of creep along. It would take a pixel, look at the surrounding pixels. If they're and basically take the average of them and then replace them all with the average. That is kind of the gist of it, right? So maybe I take this brown guy, for instance. I'm going to get the surrounding pixels, right? I'm talking about immediately the adjacent ones. You could do rows, you could do columns, but I'm just going to, for the sake of example, say everyone surrounding it. I'm going to get the average of the color there and then replace all 9 of those with what the average is. And so you get literally an averaged out type of image. But what you end up doing by doing that is taking pixels that were different, only by a little bit, and making them the exact same. Then you have a lot more duplication, right? You have duplicate pixels, so you can come back in with your run length encoding and reduce the file size from there. Now, here's the thing. By averaging those pixels out, I've lost some data, right? If I give you the number 297, and I told you that was the result from 3 numbers, that was the average from 3 numbers, can you give me the original 3 numbers? No. So there's no way to kind of undo that operation. That is why it is lossy. We have lost the information. We cannot decompress it into the exact original because we have taken an average of the pixels to get kind of an average color. Now, the thing is, by doing this, it is massive savings. This is incredibly, I'm like just skipping past this. I'm telling you the gist of all this. Right? This is used for multimedia files such as images, videos, audios, where it doesn't really matter. Now, this is very zoomed in effectively in terms of your pixels, right? I can like literally see the pixel. But you're viewing this on a screen that has millions of pixels. If we were to just zoom in on the screen, we would get down to these little tiny dots, right? But when you zoom out, you can't really tell. You can't really tell that one of those dots is just a little bit different than the one next to it. So when it comes to images, audio, it's hard for users to really tell that there is some information loss. So it doesn't matter as much that you can't get back to the exact original. The upside here is these file formats, JPEG, GIF, MP3, etc., are massively compressed, right? Where we were getting, like 50-60% compression on a video, in our text file, a video can get something like 90 to 95% compression, right? That's huge, right? It's huge to go from, like a gigabyte to 1 megabyte or 100 megabytes, whatever that percentage works out to be. So being able to deal with just a little bit of information loss actually goes a long way. Compression is incredibly important in the modern computing world where multimedia files are often streamed in real time over the internet, right? There's no way that I could do this video. The video you're watching right now is compressed. There's no way that you could get the raw data. You would spend too much time downloading it. It's just not worth it. By itself, video accounts for 3.6 exabytes of data every day. That is 80% of internet traffic. Right? If this stuff wasn't compressed, would that be a big deal? This is 3.6 exabytes of data with the compression, right? If it was not compressed, it's 10 times this or whatever. So what is an exabyte exactly? Well, here I have a chart kind of outlining these things. The smallest unit of measure we have is a bit at 0 or 1, right? We can represent that with a boolean. A byte, we saw with our text file, that's 1 character, and a byte is 8 bits. Probably the next biggest recognizable jump is a kilobyte, and we're talking text files are in that range, right? The text files we were looking at earlier, like 240 bytes. So like a kilobyte, you could use a kilobyte to kind of represent that. When we get into megabytes, we're looking at our images, we're looking at audio files. Gigabytes, we start getting into videos. Terabytes are now basically where our hard drive ranges are at. You can probably get like half of a terabyte, that is 500 gigabytes. But for most part, we've moved in the terabyte range. A petabyte is, we're talking like a database, multiple hard drives worth of information. And exabyte, when we get up to that range, we're talking internet traffic, data that is measured. This is daily, right? This is 3.6 exabytes daily is the amount of internet traffic, right? That is, we're talking 1024 is one, the petabytes is 1 exa. This is huge. This is like huge information. By the way, this number, 1024, that's not a coincidence. This is a binary number, right? This number comes from that. So let's recap. With blank compression, all of the original data can be recovered when decompressed. That's going to be lossless. List 3 file formats that use lossless compression. Oh, I zoomed past those. I don't quite know off the top of my head. I'm thinking like text files. There are going to be some image files, right? Image files I'm thinking are like PNGs or bitmaps. This is Microsoft Excel, by the way. Blank is a lossless compression technique in which a sequence of duplicate data is replaced with one instance in a count. We're talking lossless compression. I don't really see any reference to images, but we saw it with images. We saw the concept with images. You could, in theory, use run length encoding to compress something else, a text file. For instance, you'll probably have a lot less success than our traditional dictionary cataloging style technique. Blank compression reduces a file by permanently eliminating certain information, especially redundant information. This is going to be lossy compression. We do lose some data. List 3 file types that use lossy compression. Lots of images. JPEG, I know you're all familiar with the deep fried nature of a JPEG. That comes from the lossy compression. Other things include a GIF, audio, such as MP3, AVI is a video format, as well as MPEG. Lots of lossy compression going on. Blank compression should be used when loss of information could pose a problem, such as with text documents and spreadsheets. Lossless, there I can't afford to lose data. Order the following file sizes from smallest to largest. Order the following file sizes from smallest to largest. We're looking at gigabyte, kilobyte, petabyte, terabyte. I'm going to go back to my chart. All right. Kilobyte is going to be our smallest out of those, followed by giga, tera, and peta. Okay, that is going to wrap this one up. I'll see you in the next one.